now actually picture is wrong. It's not Sara. Okay, but you can see Sara here. Okay, great. Now we have our second speaker. So Professor Sara, every time I have to Magliacane. So Sara is currently a assistant professor at the University of Amsterdam. Prior to that, she was a research staff member at MIT Watson AI Lab, IBM MIT Watson AI Lab. And she has been focusing on various aspects of causal inference and symbolic approaches, and had done very exciting work in dealing with non-stationary data, the connection between causality and machine learning, and reinforcement learning, and so on. And actually, she is active in causality research in multiple ways. She is actively involved in the organization of a number of conferences, and actually she's a research hub in the field. So she knows every research advance and everyone in the field. So Sara, now it's your time.
So first I wanted to thank the organizers for inviting me. For some reason, just a second, this is already going to work on its own. So I wanted to thank the organizers for inviting me, especially Professor Zhang. And you know, he has an issue pronouncing my name. I have an issue pronouncing his name, so I think it's fine. We try our best. So I wanted to talk to you about causality-inspired machine learning, which is a way that we were proposing how to call a certain type of causality, which actually is helpful for machine learning. And I wanted to check, is the audio okay now?
Good.
Okay, perfect. Let's see. Okay. So I think here it's a bit preaching to the choir. We all agree that the real world has a lot of issues. So machine learning a lot of times has a lot of assumptions that they're not true. So they're biased data. Not everything is i.i.d. And sometimes we want actionable insights. So we don't want correlations. We want actually causal insights. And I think in this community, we also all agree that causality is already helping a lot with several of these questions. And in particular, it's kind of a systematic way to fuse data and reuse biased data, even when they are not i.i.d. And it's also a systematic way to extract actionable insights. Okay, so up to now, we're happy. In this talk, I'm going to argue like something maybe a bit slightly controversial. You can decide. And the idea is that sometimes full causality, in which I mean that we go and find the true causal graph, is maybe not necessary. Maybe we don't need the whole causal graph, and maybe it's too expensive because we meant to find the whole causal graph. And so I'm going to talk about this causality-inspired, which is, in a sense, the inspired is like a way to say it may have causality, but not necessarily. So it's a bit of a kind of causality light thing. And in particular, I have an example from the main adaptation that I will talk about in this work. But obviously, I wanted to point out that it's not just me doing this. There's a lot of people doing this, especially Professor Zhang. So first, I wanted to maybe point out some quite kind of obvious connection between transfer learning and causality. So in transfer learning, we care about predicting what happens when the distribution changes. For example, if we have a self-driving car and it's been trained in US, people drive on the right. You want to also use it in UK where people drive on the left. So there is a change and we want to be able to adapt to that. And in a sense, in causal inference, we also want to predict what happens when the distribution changes. But usually we assume that we want to predict it, what changes after an intervention. And then there is the very well-known do calculus for seeing what happens after when you have a perfect intervention. But there are not only perfect interventions, so there are also soft interventions. In soft interventions, you don't necessarily fix X to a certain value or make X independent of its parents, but you change essentially the distribution, the percentage distribution of X given its parents. So I'm going to argue that this is a very general setting, and this can also model changes in distributions which are not from real interventions. For example, because you have data from different observational setting or different labs. And so there is some connection between causality and transfer learning. And as I said, this is not my idea. This is not a new idea. This is at least the first paper that I found in which we were already discussing this. And you can see some familiar faces, familiar names actually here. For example, Professor Zhang. So this is already from 2012. And there has been obviously a lot of work since. And let's say one of the base hypothesis of my talk is that causality allows us to reason systematically about distribution shifts. And here I collected some more recent works, as you can see from several different groups. And I did kind of have some selection bias and selected some of the works, all of which were using actually graphs. And so I'm going to talk a bit about how you can reason about distribution shifts through graphs, just to give an idea. And I wanted to point out that this works also if you don't know the graph, so the graph is unknown. And in our case, we also had the setting in which you didn't have any label in the target domain, so a zero-shot setting. And this still actually allows you to reason systematically. So I'm going to start by giving you some examples. In particular, so in that work, we'll focus on this unsupervised multi-source domain adaptation case, which will be my running example. So let's assume you have some data from a source domain. For example, you have some data from some mice. So each row is a mouse, and each column is a feature, for example, x1 and x2, and we have a label y. And in the source domain, we know everything about these mice. But in the target domain, there has been some intervention, some change on the mice. So these mice are genetically modified, so they're different. The distribution is different. And for them, we don't know any label y. So that's why it's unsupervised. There are no labels in the target. Now, the task is we want for the data in the target, so for the mice which have been genetically modified, we want to predict the label y from their covariance. And we also want to use the data from the normal mice, for which we do have, obviously, the features and the label. But we have to be careful because there is a distribution shift. So we'll need some assumptions for this. But this is the task we're going to focus on. And I wanted to say that, people have already done domain adaptation from a graphical perspective, at least since 2013, especially Professor Zhang. And one simple way, this is very simplified, one simple way is that we can add the domain variable d for each of the mice. And so the variable d just represents for each row, where does the data come from? For example, 0 could be the normal mice, and 1 could be for the mice which have been genetically modified. And then we can simply see this data, which technically come from different distributions, as if they were coming from a single distribution, p of x, y, and d. So x is just, bold x is just x1 and x2, etc. And for example, this can be also represented with a causal graph, this one on the right. And so in this case, this would be, I don't know, this would be the generative graph of the data, or the causal graph underlying the data. And this can be possibly unknown. So if it's unknown, what can we do? We can steal relations and conditional dependencies from the unknown graph to reason about invariances. So this is what we'll see in a few slides. And just to convince you, this is just a very quick example. I'm going to give the organizers the slides, so if you want to check the details. But this is just an example in which we have 3 structural causal models, which are essentially the same. The only difference is the equation, which is colored in different colors. And so we can say the first one is domain 1, so domain 0, domain 1, and domain 2. And this means we can put them together in a single structural causal model if we just use D as a kind of switch. And so now we can add D to the graph. And this is just to show you that the thing I showed in the previous slide is okay mathematically. And so for the domain adaptation case, we can consider, for example, the first 2 domains as observational, so as source domains. And for example, the first one can be observational data. And the second one, for example, could be a perfect intervention because we fix x2 to 1. And then we want to predict what happens in the target domain, which is, let's say, for example, a soft intervention based on from the first domain. If the first domain is observational case, the second domain has a slightly different function for x2. So it's like a soft intervention. So just to give you an example here, in this example that I just told you, I just plotted the distribution of y, which is the variable in the middle, given x1, which is here, in each of the domains separately. So these are scatter plots. And you see the scatter plots, they look more or less the same. So we have x1 on the x-axis and y on the y-axis. And so this is, in a sense, an empirical proof that this distribution is invariant across the different domains. Now I'm going to choose instead x2, which is here. So we have y causing x2, but x2 also changes in the domain. So that's why the domain has an arrow to x2. And now we're going to see that the conditional distribution of y given x2 is not invariant. So in this plot here, we have x2 on the x-axis and y on the y-axis. And we see the different colors are the data from the different domain. And so you can see if we were to use only domain 0 and 1, which are here, to fit a line, we would fit a line probably in the middle. This would be a very bad approximation or a very bad prediction for the data in domain 2, which is quite different. And here I have also like a numerical example, if you will later see the slides, in which it shows that essentially the error becomes arbitrarily big. And just to give you an intuition why this happens, so this is actually, if you know a bit of this separation from this graph, this is all obvious. So this invariance between, so the fact that y condition x1 is invariant, we can write it as the probability of y given x1 given d equals 0, so one domain, is the same as the probability of y given x1 with d equals 1 and with d equals 2. So if we say that these are all the same and they're all the same as just the probability of y given x1, this is the same as saying as y is independent of d given x1. So this is the definition of independence. And so we can say that this y is independent of d given x1. If we had the true graph, we would be able to read it from the d separations in the causal graph, because we have y and d. When we condition x1, y is d-separated from d because it's already d-separated. You don't even need to condition x1 because the only path between them is through this collider here. So x1 is a good predictor of y. And in this case, it's also invariant across the domains on its own. So this is just using this separation, we can reason about what will be invariant. And just to, really hammer in the point, with x2, this is not happening because we have this path between d through x2 to y, in which x2 is a collider. So when we condition it, this path becomes open. So y and d are d when we condition x2. And this is also shown by the fact that the conditional distribution of y given x2 in the different domains is not the same. So essentially, this separation allows us to tell which distributions are invariant across the domains. And as I said, this is not a new idea. This is other people have already discussed this. So, and we call it, in our work, we call it separating features, the features which have this property that de-separate y from d, but other people have called them stable features or invariant features. So this is a general concept of what we care about and what we probably want to look for. And when we have the graph, this is easy, literally go and check the d-separations. But the interesting part is when we don't have the graph. Before we go into not having the graph, I just wanted to point out a few quick things that, having a graph allows you to realize that you wouldn't if you didn't have a graph. So sometimes people think, I'll just take features which are invariant across, many domains, and many source domains, and this will be okay in my target domain. And in this example here, we have cases in which we can have features that are invariant. Sorry, this is the other misconception. I got confused with myself. So this is a misconception that if you want something that is invariant, it needs to be causal. And in this case, actually, you have that both x1 and x2 are invariant. So y conditional x1 and x2, its probability is invariant across the domains. And you can see this from this separation and independence here that we assume are going to be, these separations and independences are going to be the same, even if x2 is not a cause of y. So causality is not necessary. But this doesn't mean that, if they're invariant across many domains, that they will be causal. So this is in both directions. And so if you want to use invariance to find causality, then you need to use this algorithm from Peter et al. 2016, which then does an intersection of the things which are essentially separating sets of features. So they separate y from d. In this case, the intersection of x1 and x1 and x2 is x1, and x1 is indeed causal for y, so it's apparent. And another discussion is, so sometimes people want to discuss generalization, and they think that if they are going to find features that generalize to any change, they will be fine with causal features. But there are cases in which you have latent confounding. So maybe there is a hidden variable here that causes both x2 and y, which I represent here with this bidirected edge. So if you have this case here, then you don't want to use x2, which is a parent of y, to transfer across the domains, but you want to use x1. And this is very similar to the instrumental variable case that was already mentioned in the talks before. And so in some cases, the parents also cannot help you for generalization or adaptation if you have latent confounding. So concluding, why did I discuss both of these? I wanted to just bring you some essential examples or counterexamples in which I can show that causality is not necessary because some non-causal features are also invariant, and it's sometimes not sufficient in this case because there's relative confounding for transfer. And so instead of discussing causality, I'm going to focus on these separations and independencies. So here I'm going to list like a list of properties that are actually, it's a list of properties that the causality-inspired domain adaptation method should have. And it's a bit cheeky or funny because it's obviously the properties that in the form show that it has. So it's just essentially a nice way to organize the properties that the algorithm has. So we would like an algorithm which is able to work when the graph is unknown. It's able also to discuss, to allow for latent confounding, and it's able to avoid parametric assumptions. And this is a bit of a specific case. So instead of modeling changes between each domain, which is what I showed you with the D variable, we're going to use a kind of a set of indicator variables so we can disentangle the sources and the target. And this is a very simple point mathematically, but it's very useful for our method to actually be able to do some things that other methods didn't do. And I'm going to explain more in detail. And then we're going to avoid this assumption that you're going to hope that if something works in the source domains, it also works in the target domain. So our method will also try to use some data from the target domain in order to be able to avoid this assumption. So we're going to focus on unsupervised multi-source domain adaptation. So this is from our work in 2018 in NeurIPS. In this case, we have again the mice example, but instead of having only one set of mice from the source domain, we have two different source domains. So normal mice and genetically modified mice where gene A has been intervened on. And then our target is another gene, gene B. And so these are all different types of mice. Their distribution is different. So there are samples for different distributions. And again, as I mentioned, instead of having a domain variable D, as I showed you before, we're going to use multiple context variables, C1, C2. I'll show you what I mean. And specifically, there will be one specific context variable that will be dedicated to the target domain. And we'll see the change in the target domain as a soft intervention. And we'll have also some assumptions, for example, that Y in the target domain cannot change directly, because otherwise we won't be able to recover it. If there is nothing, if it can change arbitrarily on its own in the target domain, it's a bit of a hopeless case. And now the graph is unknown. Yeah. So we're going to use this other work we had, joint causal inference from 2020, GMLR. And in this work, it's kind of a complex work, but in practice, the idea is very, very simple. In that work, we assumed, again, as I mentioned, we have data from different distributions, and we're going to just merge them together. And the way we merge them together is by adding context variables. And context variables will be, for example, there will be an encoding of each domain. For example, we'll use 0, 0 for the observational domain, 1, 0 for the second domain, and 0, 1 for the third domain. So for example, C1 will be 1 in domain 1, C2 will be 1 in domain 2, and 0 otherwise. So they're just indicator variables, dummy variables. And why do we do this? We do this because then we're going to pretend that C1 and C2 are just normal variables, normal random variables. They are not, but we're going to pretend so we can reuse a lot of the work that people have done. And we can also add some additional knowledge that C1 and C2 are not caused by the other variables because we have added them essentially. So this means that now we're going to just treat these context variables as normal variables. And what we usually do in causal discovery, especially in constraint-based causal discovery, we do conditional independence tests. And then based on the conditional independence tests, we assume the conditional independence tests are constraints in terms of these separations on the graph, on the possible graphs that are there. And so C1 will be just treated as a normal random variable. And that's why it's also here in the graph, we also have C2 and C1. Both of them are just normal random variable. And this is C1 and C2 were together represented as D. But the difference of splitting them is that now we can isolate the target domain. In this case, this is not yet the target domain, but when we have question marks, we're able to isolate the target domain specifically. And if there is no missing data, we can get some kind of Markov clearance class. But in our case, we'll have essentially some missing data in the target domain, so we'll have a bit of a larger set of graphs. And again, as I mentioned before, what we're going to look is separating features. So sets of features that separate y from, in this case, specifically, the context variable C1 that represents the target domain. So before we had y is separated from the domain D given a subset of features S. Now it will be separated from just one context variable, because this allows us to just find things that are transferring to the target domain. And other people have called these separating features in many other ways. So in this example here, we have that x1 is a separating set. So if you have C1 and Y, when you condition x1, so this path through C2, x1 and Y is closed when you condition on or take x1 as a separating set. And instead, in the other path through x2 is usually closed. But if we take x2 in the separating set, this will open this path. So x1 and x2 together are not good because they will be, the conditional distribution will be shifting essentially. So if we don't know the graph, we could try to do the conditional dependencies, but in our case, we have them, some of the data are missing, so we cannot see how why the label changes in the target domain because it's always missing. So in this case, one simple idea is to, as I mentioned, to try to see what happens in the source domains where you have full data and just find things that work in the source domains and hope for the best for the target domain. And here I had a counterexample in which features which are separating in the sources will not work in the target. So in this case, we have x1 and y on this graph, and this is the source domain. So the green data, different shades of green are two source domains, and both x1 and y, both x1 and x2 here, they have essentially the same distribution as source domains, but only x1 has the same distribution as in the target domain, which is the blue data. So in this case, we have x2 in the target domain has a completely different distribution than in the source domain. So if we just judge from the source domains, we'll say, yeah, x2 is fine, but actually in the target domain, x2 is a problem. And this is because there is a collider bias coming from in the target domain that isn't there in the source domain. And so our idea is, let's not just use only the data from the source domains. We also want to be able to use this data here, except the one from Y. So we're going to use conditional independencies, the ones we can do. For example, we can see if x1 and x2 are independent between each other in essentially the mixture of the domains, or if they're independent in each domain separately, or in the source domains versus the target domain. So this is what we're able to do. And with these independencies, we have a lot of assumptions which can be very technical. And we have an example, which is also in the paper, in which we can prove that this works. But essentially, we're going to throw some assumptions that we have. The query, for example, is x1 a separating feature, and all the conditional dependencies that we can test. And we're going to use a separation. So in logic, all of this will go into the theorem prover, and the theorem prover will give us three possible answers. Yes, x1 is provably separating, so it's separating in all of the graphs that fit the data, or no, x1 is not provably not separating, which means it's not separating in all of the graphs that fit the data, or not identifiable, which means sometimes it's not separating, sometimes it is, we don't know. And so we can use this, essentially this check, which checks which sets of features are stable in a feature selection algorithm, for example. So this is what we're doing. So we use the source domains to find features, and then we use all of the data, including the target, to prove which of the sets of features, and in this case, we also use the context variables as features, were okay and which not. So once we found the set of features which was provably separating, we can apply it on the source domain data, and we can prove that there is a bounded generalization error in the target domain. And so this is, thanks to the joint causal inference, we were able to say that all of these different desiderata were met. Most importantly, this one, in which we are modeling the changes between the domains in a disentangled way, so we can disentangle the target in a sense from the sources. And we were also able to use the other, satisfy the other constraints. And specifically, we don't need to find the causal graph. We just care about finding a disseparation that fits the data. So this was the idea. And that's why it's a causality-inspired method, because we don't need to find the graph. We just care about the disapparition in this case. And obviously, there were many limitations for this work, especially scalability. And logic-based methods, they're very nice. They're very flexible. They allow to encode a lot of background knowledge, but they can be not very scalable. So they work on tens of variables. So this is an issue that I would like to focus on in the future, how to improve the scalability of logic-based methods for causal discovery. And just as a very quick sneak peek, because I'm worried I'm a bit over time. So we applied this to many tasks in reinforcement learning. I hope Xiao maybe mentioned it already. So we worked a lot on learning factored MDPs and PONDPs and how to use this data in these cases. So we had some work on ADRL, which was in iClear or ICML last year, 2022. And then we had also some work which was just accepted to Koen was mentioning before, on factored adaptation for non-stationary reinforcement learning. So in this case, we essentially learn a dynamical Bayesian network, or if you prefer, a factored MDP or PONDP with some latent factors. And the latent factors are able to model the changes, the non-stationarity. And it's a very similar setup in both papers. And that's very exciting because a very similar setup actually allows us to improve a lot in the adaptation case. So this is just a conclusion that this separation is really important for the reason about invariances. And people have known this for a long time. And this is true even if we don't know the graph and even if the data is missing. So this is my conclusion. I wanted to thank all of my co-authors, which are many, and some of them are actually here. So any questions?
Oh, wonderful. Thank you very much, Sarah. It's great. It's comprehensive. At the same time, it's nice that you really gave a lot of credit to others, a lot of other people. I know you started working on this problem very early, and it's a great job. So now it's time to take questions. Okay, you may raise your hand or just leave your questions in the chat box.
And I can also answer by email if people have questions. I know it was very fast. I speak very fast. So if people have questions later on, they can contact me later.
Actually, at the beginning, before the talk, Sarah was worried whether the talk would be too long. Actually, it's perfect. It's just perfect. Okay, so maybe I can ask a question. So basically, you can see here in this conference, some people believe that you can use the graphical representations, and some people don't believe so. And for instance, in Professor Zhou's talk, right, you didn't see a graph. So do you have? But we are used to using graphs to represent some relations and make use of some of the relations, right? So do you have any idea to share with our audience regarding when you can use a graph and when probably you shouldn't use a graph?
I think it depends. I mean, I think the graphs or no graphs, they represent similar ideas. For me, a graph is very intuitive. I'm a visual person. So I think maybe it also depends on the personality style. There are like some issues with graphs, which, for example, Phil David has extensively wrote about. If there is a faithfulness violation or some extra conditional independencies, you won't see it in a graph. So the graph doesn't allow you to see many things. But if you have a setting in which you don't have faithfulness violations, then I think it's nice for me at least to have a graph. And for me, it's very easy to reason about it. A lot of people work on transfer learning, and sometimes they make very simple mistakes that would be easily avoided if they had a graph. So I think a graph is a tool that allows you to reason about things, but all tools are useful. Depends on the problem.
Great. Yes, actually, why did I ask? Because a lot of people who basically started their causality research may have this question, right? In some in some of the talks, right, there's no graph, but in some other talk, you can see a lot of graphs. So perfect. I thank you very much for sharing. And okay, so if you have questions, please just reach out to our speaker, Sara Magliacane, by email. And actually, you can really get to know a lot of things from her. Thank you very much, Sara.